about the efficiency of an algorithm, we really care about the growth. So meaning that it's not the absolute number that matters, we care about how fast it's growing. Now, why is the growth important? So let's say we compare two algorithms. So just now we arrived at an expression in terms of n, right? Now let's say you have two algorithms that solve the same problem. So there is the blue algorithm that will run 3n, meaning if your n is the number of input, the input size, so your algorithm needs 3n in terms of number of operations. Now you could also have a different algorithm that is n squared divided by 3. So then it's going to have, if your n is the input size, so your number of operations is going to be n squared divided by 3. Now if you plot them on a graph, it's going to look like that in terms of how it's growing in terms of the input size. Now if you are given these two choices, right, which one do you consider to be the better algorithm? Blue or red?
Blue.
Blue. Alright, so why blue?
Red increases exponentially.
Okay, we don't call this exponentially. It increases fast because exponentially there is a different function that increases exponentially. Now in this case, it's true that blue increases slower, right? Now if you are comparing, then but you can say that when the input size is small, the red one is actually better, right? So why isn't the red one a good algorithm? So when you run things on a computer, right? We are talking about, computers today are generally fast, so they run in a small amount of time. Now, when your input size is small, different algorithms may still have different running speeds, but they're all small. So meaning we might be talking about the difference between 1.1 second and 1.2 seconds, and these kind of differences don't actually matter. So what actually matters is the differences when the problem is big. Because when the problem is big, then you're talking about differences in terms of hours, maybe even days. It's for your algorithm to actually finish. So which is why when we compare algorithms, we don't pay attention to the part where the input size is small. It's irrelevant. Something may run a bit faster when input size is small, but most of the time it doesn't matter in terms of the total amount of time that is taken. So we're going to focus more in terms of when the input size is big. Now, not only that, we actually want to see how will it actually compare as the input size get as big as possible. Because you realize that as the input size is growing, the difference between them is actually growing. So the difference is going to get larger and larger. So that's what we call asymptotic order of growth. The asymptotic here simply means that we want to push things out to the limit. So we want to compare algorithms when the input size is the largest possible. And when they're the largest possible, then only certain things are going to matter. Now, what is an example of that? Okay, later we're going to see an example of that. Now, let me just make one more point about the worst case, best case, and average case. So when we talk about an algorithm, there are different cases in which the algorithm runs. So for example, right? So let's say if I want to find out who here has a motorcycle, let's say. So I just need to know at least one person who has a motorcycle. Now I can employ an algorithm where I just ask each one of you one by one, right? So I'll ask you, do you have one? Do you have one? Do you have one? And as soon as I find one of you that has one, then the problem is already done. Now, in the best case, the first person I ask will say yes. So then I stop there. So I never need to look at anything else, right? Now what's going to happen in the worst case? So I ask everyone, and either the last one has it or nobody has it. So I have asked everyone and nobody actually has one. Now, essentially it's the same algorithm, but depending on what happens in actuality, depending on the data that you end up with, there is a best case, there is a worst case. Now, when we analyze algorithms, we always focus on the worst case. We don't focus on the best case. So why? Because the best case may just be because you're lucky to get a best case, but in reality, when you face problems, you don't have any choice in terms of what case you actually get. Now, what would be more meaningful, actually, is to look at the average case, right? Because in some sense, you may have a problem and you want to see on average how many people you need to, For example, in the earlier example that I asked you, if I just want to know who has a motorcycle, if I do this every day, all the time and so on, I can average out Sometimes I'm lucky, it's the first person, sometimes it's the second person, sometimes it's the third person, and so on. Now, if it is all uniform, then I'm going to get about n over 2. So by the size of the class divided by 2, that will be the average. Now, this kind of case is relatively simple to analyze. But for most of the other problems, it depends really on the underlying distribution of the input. So it's very hard to quantify what is the average. Because when we need to, in order to know the average, we need to know the full distribution. So because it's difficult to analyze, we don't usually analyze algorithm based on the average case. Worst case is more definitive because we know what's going to be the worst case. And luckily, most of the time, if you get a worst case right, your average case is actually very similar to the worst case. So meaning that a problem that is difficult to solve in the worst case is also difficult to solve on the average case. So from now on, we are going to focus on just the worst case. So every time you see an algorithm, figure out what is the worst case. Now, in 3 steps, then you can figure out what is going to be what we call the big O notation. So the 3 steps are, so first, you need to look at an algorithm, figure out the worst case. The second step, you need to count how many operations you need to do to solve the problem for a given size of n. Now, in the worst case, so you have identified the worst case, you have counted how many operations you need to do in the worst case. Then the third thing is what we call the big O notation. You need to reduce the number of operations into something that we call the big O, which is a notation to indicate how complex is the problem that we are dealing with. Now, the big O is written in this way. So it's going to be O and then parentheses and then some function of n. N here is always the input size. Now, when we say something is O n squared, it means that the algorithm that we have is going to have an order of n squared. That means as n goes larger, the number of operations will be roughly n squared. Now, when we compare algorithm, as long as they have the same kind of big O, we consider them to be comparable. So we have algorithm 1, algorithm 2, both of them are O n squared. We consider them to be more or less the same in terms of the complexity. Now, what are the different big O cases that you will encounter? Now, one of the cases that you're going to encounter is what we call O1, which is constant time. Now, in this case, you can increase the input size, but the number of operations actually remain constant. Now, this is the best kind of algorithm that you can get because you keep increasing the input, but the complexity always remains the same. So that means that it doesn't actually affect the runtime. Now, another kind of case is what we call linear time. It means that your operations are going to grow at the same rate as the input. So if your input were to double, then the number of operations would also double. Then we have something called quadratic, which is not increasing faster. Cubic, which is n to the power 3, even faster. Now, this is a table that's given to you to have an initial sense of which kind of complexity is actually more higher, as in like more complex. This is given in terms of increasing order of complexity. Now, O1 is the simplest one, and then you have O log n, On log n, On to the power of something, which is n to the power of 1, n to the power of 2, n to the power of 3. And then we have something called exponential. Now, when we say something is exponential, it means that the function is k to the power of n. K here is some constant. So for example, 2 to the power of n, that's exponential. 3 to the power of n, that is exponential. Now, the largest one is n factorial. So n factorial is a very large number because if we talk about the growth rate of different functions, it turns out that when you increase the input size, the number of operations you need is going to grow at different rates. So O1, it means it doesn't grow. It stays constant. Log n, it means that when your n doubles, number of operations will increase by 1. So On means that when your n doubles, it's going to go linear. So you're going to increase at the same rate, it also doubles. N to the power of 2, when n doubles, your operation is going to go square to the doubling, which means that it's going to increase 4 times. So to the power of n, it means that n increases by 1, the number of operations doubles. So that's the opposite of the log n. And finally, n factorial, and n increases by 1, the number of operations increase n times. So increasing your input by 1 will increase the number of operations you need to do by n times, which is a very large number. Okay, now the reduction to the big O will follow what we call the dominance rules. Now these are some rules of thumb that you will need to get a sense of, and with practice you're gonna find it quite intuitive. But one of the things that you need to understand is that when you have multiple terms, you only keep the most dominant one. So it means anything less than the most dominant one, you can drop it. So if it's 2 to the power of n plus n squared, 2 to the power of n happens to be more dominant, you drop the n squared. N squared plus log n squared is more dominant, you drop the log n. Now, if you have multiple functions, each of them of the same order, which is polynomial, but they have a higher power, for example, then you only keep the one with the highest one. And we ignore the constant. So like 3n squared, we just drop the 3, so it becomes O n squared. Now you follow some of these rules, then you can characterize what is going to be the big O of a particular function. Now, going back to this point, why is it that we only keep the dominant one? Now, it comes down to the earlier point that we are making about we want to push the input size to be as large as possible. That means we go all the way in the limit, what is it going to be? Now, this is an example. Okay, it's rather small. But let's assume that you're interested in 2 to the power of n and n squared, right? Now, as n keeps growing, your 2 to the power of n is growing in this way, which is very fast. N squared is also growing, but not anywhere as fast as to the 2 to the power of n. So if you look at the sum of 2 to the power of n plus n squared, the sum, because this number is much larger than this number, the sum essentially is dominated by only the first number. And essentially as a proportion, 2 to the power of n essentially is going to account for pretty much almost all of the number. So you have two numbers, one is much larger than the other one, then only the larger number actually matters. The smaller number doesn't actually matter. Now you can say that, but 2 to the power of n squared, they are still big numbers, yes, but as you push n to the limit, then one of them is going to be much, much larger than the other one. And that's why we always drop the less dominant ones. Right? Now, steps towards the big O. So remember, 3 steps, right? So first, we are going to characterize the worst case. So you have an algorithm, you find the worst case. And then you want to count the number of operations you need to do for a particular input size n. And then you reduce it by dropping the less dominant terms. Now, why are you interested in complexity? So once you have the complexity of an algorithm, what can you do with it? So it turns out there are some useful things that you can do with this information. So one of the information that you get is the difficulty of a problem. So if you want to know, can I actually solve a problem? How difficult is this problem? So one way to do it is to look at algorithms that solve the problem and see what is the complexity. The higher the complexity, then the more difficult the problem is. Now the second information that you get out of it is comparison across algorithms. So if you want to solve an algorithm with lower complexity, it is usually preferred because it's going to run faster in general. And the third information you get is whether a problem is even solvable or solved. Now, the way we think about a problem in terms of being solvable is whether there is an existing algorithm that can solve the problem in polynomial time, all below. Now, polynomial means n squared, n cubed, n4, and so on. If the best algorithm you have is exponential, which is 2 to the power of n, or even factorial, which is n factorial, we don't consider it solvable. Why? Well, because these kind of problems are much too complex. Because if you look at the comparison, right? So this is a chart that looks at the input size and how fast it's growing. Now, you need to bear in mind that these are actually log scale. Log scale means that every time you go up a notch, you multiply the number by 10. So this is 1, 10, 100, 1000, and so on. So this is this is factorial. Now, factorial is growing much faster than any of the other complexities. Exponential is also growing much faster compared to the rest. So then these two, we consider them to be unsolvable. So if you have an algorithm that runs in exponential time, that runs in factorial time, you cannot actually run it. It's not actually feasible. Now, why do we say that? Now, let's look at this comparison, right? So let's say you have a computer that can take one operation in 1 nanosecond. So then this is the input size. And this is your algorithm and how much time they're going to take to solve a problem. So if your algorithm is log n, you can push your input size all the way to 100 million. You still take less than a microsecond to solve the problem. So that's very fast, right? So no problem. Now, if your algorithm is n, then when your input is 100 million, it's still less than a second. So it's still okay. Now, if it is n log n, you still talk about 2-3 seconds, which is still okay, right? Now, by the time you talk about n squared, to solve a problem of 100 million, you need to wait 3 months. Now, are you going to actually wait 3 months? So probably you wouldn't wait 3 months, right? So in that sense, so the issue here is not the time. The issue here is going to be how big a problem can you solve. So if you can wait 20 minutes, then you can solve a problem of size 1 million. If you cannot wait even 20 minutes, then you are going to solve even a smaller problem. Now, if you look at the last two columns, to the power of n, n factorial. Now, to the power of n, even when your problem size is 100, it already takes 4 times 10 to the power of 13 years, right? So that's not possible. We can't do that. Now, which means that in practice, the largest problem size you can solve is about 40. Because even waiting 2 weeks for a problem, you may or may not be willing to do that. Now, if your algorithm is n factorial, then even size 20, you already take 77 years. Right? So you hit the run button, right? Your grandchildren will see the results, right? And then they will find a bug and then they have to start all over again. So it in effect means that the problem size that you can do is only size 20 or even less, right? Maybe even just size 10. Now, so we consider these two problems to be very difficult to solve. Now, which brings you to the options that you actually have. Because if you're trying to solve a problem and you cannot compute it fast enough, what choices do you actually have? Now, one choice is to buy a faster computer. So if your algorithm is n factorial or to the power of n, it can solve size 10 or size 20. If you buy a machine that is 1,000 times faster, then you can increase the problem size from 10 to 13, from 20 to 30. So that's one option you have, right? So if you buy a computer that's 1,000 times faster, you can only increase the problem size that you can deal with by a little bit. But if you manage to bring down the complexity of the algorithm, so instead of n factorial to the power of n, you go to n cubed, n squared of n, then the problem that you can solve within 1 second can actually be much, much larger. So it's much more practical to try to design a better algorithm than it is to try to find a faster machine. So most of the time, if your algorithm is too slow, the problem is not the computer. The problem is the algorithm. Alright? So now essentially this is the most important concept in all of computational thinking. The concept of complexity. So from now on, it's going to appear again and again. The very basic idea that you have a problem, you need to design an algorithm to solve it. Now, once you have an algorithm, you need to count. You need to figure out what is the worst case. And then you count how many operations it's going to take in the worst case. Then you reduce it to the big O. And that gives you a notation in terms of O. What is the complexity of the algorithm? Then there are more things you can do with it to try to compare different algorithms, for example, or to try to see whether there is a need for you to try to bring down the complexity even further. All right? Now, so far, any questions about this concept of complexity?